Okay, so we had found the Laplace transform of our solution to this lovely differential equation was this. And we said this we could break up into its partial fraction decomposition, and we were in the process of doing that. So here was the general form of the partial fraction decomposition, and we had cleared the fractions, multiplied everything out, and so now we're ready to equate our like coefficients. So I've got four types of terms. I've got s cubeds and s squareds and s's and numbers. I'm going to get a system of four equations and four unknowns. It's not going to be as bad as it sounds because not all of the variables are going to show up in all of the equations. And if you notice that I only have a number on the left-hand side, a lot of these things are going to have a zero on the left side. So it's going to be a relatively nice system of four equations and four unknowns. If I look at the number of s cubeds that I have, on the left side I have none, and on the right-hand side I have a plus c. Now that's super nice because that means that c is the opposite of a. So right there I'm down to three unknowns because I can replace c with the opposite of a whenever I feel like it. Okay. If I look at the s squareds, on the left-hand side I have none of them. On the right-hand side I have 2a plus b plus d. Okay. If I look at the number of s's, on the left-hand side I have none. On the right-hand side I have 4a plus 2b plus 4c. I'm liking that because c is the opposite of a. So that's 4a plus 2b minus 4a. So that's telling me that 0 is equal to 2b. 2b. That's telling me that b is equal to 0. So as I solve for these things, let's record them. I've now got that b is equal to 0, and I've still got to solve for the remaining ones. Now if I look at the number, now on the left-hand side I actually have something. I have a 2, and on the right-hand side I've got 4b plus 4d, but we just figured out that b was 0, so that's 0 plus 4d. So that's telling me that 2 equals 4d. Okay, d is 1/2. We're halfway there. Okay, so now let's take a look. If I come back to this equation, 0 is equal to 2a plus b we just determined was 0 plus d we just determined was 1/2. So that's going to mean that 2a is negative 1/2, a is negative 1/4. And c is the opposite of a, so that's going to be positive 1/4. Okay. So, wasn't quite as bad as it might have been. Okay. What I'm going to do, just to not use up too much space on the board, is I'm going to rewrite this, plugging in the values that I got for a, for b, for c, and for d. And I think what I'm going to do as I do that, it was e to the negative 5s times this sum. I'm just going to distribute that to each piece. So I'm going to have e to the negative 5s times as plus b is going to be negative 1/4 s plus 0 over s squared plus 4. And then I'm going to have plus an e to the negative 5s, because I'm going to distribute that, times this fraction, cs plus d, is going to be 1/4 s plus 1/2 all over s squared plus 2s plus 4. Okay. So that now is my Laplace transform of y. And what I want to do now is try to make each piece match one of my formulas for a Laplace transform so that then I can easily apply the inverse Laplace transform. Okay, so if I take a look at this piece, okay, notice that was an irreducible quadratic. So I've got a number on top of an irreducible quadratic. But I know that what I want to do is complete the square so that I can get s plus or minus some number squared plus a number, because that's what shows up in my formulas for the Laplace transforms involving sines and cosines. Okay, so just working with this, and that's going to help me out with this piece as well. I can say s squared plus 2s plus 4. Well, if I cut that 2 in half, I get 1. 1 squared is 1. So I'm going to add 1 and subtract 1. Okay. And so that's going to give me s plus 1 squared plus 3. Okay. So this piece becomes 1 over s plus 1 squared plus 3. Okay, let's see how that's going to help me out in trying to make it match one of my Laplace transforms. Okay, so I've got a number on top, and not just s squared, but s plus a number squared on the bottom. So I'm looking at formula 3 here. Formula 3 tells me that the Laplace transform of e to the at times sine omega t is going to equal omega over s minus a squared plus omega squared. Okay. So I can see my a here must be equal to -1. Okay. And that's got to be the case because I'm subtracting -1 if I'm adding 1. My omega will be the square root of 3 because I need omega squared to equal 3. Okay. So that way I've made the bottom match. Now what I want to have on the top, of course, is my omega, which would have to be a root 3. So I'm going to simply need to multiply this by 1 in the form of root 3 over root 3. Okay. And that way, what I will have for this piece is 1 over root 3 times root 3 over s plus 1 squared plus 3. That is a match for formula 3 with a equaling -1 and omega equaling 3. Okay. So I'm going to just record that information. This piece is now nicely set up for me to try to apply the inverse Laplace transform once I'm ready to do that for all of these pieces. Okay. All right, so now I move to this piece. Now notice with this piece and this piece, both of those are getting multiplied by e to the -5s. And if I take a look at formula, is it 14? It is formula 14. Okay. Formula 14 says if I started with a Heaviside function, turning on some translation of a function at some time, that's going to have me multiplying, that's by e to the -as. Okay, so this piece right here is going to use formula 14 with mu sub 5 of t. Now, I'm purposely just writing the Heaviside function rather than writing that a is equal to 5, because a shows up in formula 14, but a sort of gets recycled and it shows up in most of the other formulas as well. So anytime I'm using formula 14 so that I know that I'm going to be multiplying my inverse Laplace transform by a Heaviside function, I'm just going to explicitly write the Heaviside function. And now I want to try to make this thing match. Well, that -1/4 I'll be able to just factor out, and then I've got s over s squared plus 4. So that's actually going to match formula 7. Let me remind you of what formula 7 says. Formula 7 says the Laplace transform of cosine omega t is just s over s squared plus omega squared. Okay, so this, if I factor out that -1/4, this then matches formula 7, where my omega would be 2, so that when I square it, I get 4. Okay, so I'm going to just rewrite this piece as -1/4, just write that constant in front, e to the -5s times s over s squared plus 4. Okay, so I'll use formula 14 when I take the inverse Laplace transform to introduce a Heaviside function, and then I'll use formula 7 with omega equaling 2. Okay. All right, excellent. So now we've got this lovely piece. Okay. So I've got e to the negative 5s, which tells me that once again I'm going to be using formula 14 and the Heaviside function for 5, turning things on at 5. Okay. Now, this piece I'm going to want to spend a little bit of time rewriting. So I'm going to just sort of section off this much of the board to work with just that piece for right now. And I'm going to do two things. First, I'm going to rewrite that denominator the same way I did here, as s plus 1 squared plus 3. Second, I'm going to split up the top so that I've got two separate fractions, one of which has some s's on top and one of which just has a number on top. Okay. So if I do that, I've got 1/4 s over s plus 1 squared plus 3 plus 1/2 over s plus 1 squared plus 3. Now I'm going to work with this piece first, because I remember if on bottom I have s plus 1 squared, I'm going to want to ultimately get on top s plus 1. So I'm going to be adding and subtracting something there. The part that I add I'm going to want to keep so that I end up with an s plus 1 on top. The extra constant I'm going to combine with this piece. That's going to change the constant that I have on top here. Okay. So I'm going to just write this piece, first of all, as 1/4 of just s over s plus 1 squared plus 3. But now, if I take a look at that, okay, the denominator here is matching what I'm going to have in Formula 8. So Formula 8 tells me that the Laplace transform of e to the at times cosine of omega t is equal to s minus a over s minus a squared plus omega squared. Okay. So I can see that we're using Formula 8. My a is -1 and my omega is √3. That seems very familiar. They actually match from here because I have exactly the same denominator. But now I can see that what I want to have on top has to be the same thing that I'm squaring on bottom. So I want to have a +1 on top. So what I'm going to do is add 1 and subtract 1. When I do that, I just want to be careful because this 1/4 applies to this whole thing. So that's going to be 1/4 of s plus 1 over s plus 1 squared plus 3 minus, because of this -1, 1/4 over s plus 1 squared plus 3. I'm just going to bump that 1/4 back up to the top. Okay, so this piece I've made match very nicely. Now this piece I'm going to be able to combine with this piece to try to make this match the formula for e to the at times sine omega t, because I'll have just a number on the top. So I've got these two pieces to deal with still. Okay, let's see. I can do this. I hate having this small board. Okay, so let me just copy what I need to still deal with. What I need to still deal with is this minus this. Now a half minus a fourth is just a fourth. So I've got 1/4 over s plus 1, s plus 1 squared plus 3. But what I've gotten from this one piece here is plus 1/4 of, we still had the e to the -5s, and then times s plus 1 over s plus 1 squared plus 3. Okay, and so for this we're using Formula 14. This is going to become the Heaviside function at 5, and then we said we were also using Formula 8 with a equaling -1 and omega equaling √3. Okay, And then we're going to have this last piece here. I'm going to just rewrite this as 1/4 times 1 over s plus 1 squared plus 3. So same denominator, but I just have a number on the top. And so that's going to be equation 3 that I'm now trying to match. We'll still be using equation 14, which will give us a mu sub 5 of t, and then equation 3. Equation 3 tells me that the Laplace transform of e to the at times sine omega t is just omega over s minus a squared plus omega squared. So I can see my a is still -1, my omega is still √3. All of that still holds, but what I want to have on top instead of 1 is omega. So I want to have a √3 here. So what I'm going to do is multiply by 1 in the form of √3 over √3. That puts the √3 I want on the top, and this √3 I'll combine with the 1/4. That becomes my coefficient. So I'll have plus 1 over 4 √3 e to the -5s times √3 over s plus 1 squared plus 3. So I've got 4 terms that I have now manipulated to just be a multiple of a Laplace transform that I know and love. I've written down the relevant formulas and the relevant constants. We've been going for a while, so I'm going to stop this video. In the next video, we'll actually take the inverse Laplace transform and finally be done with this problem.